Okay, so today I will be reviewing sequences and series. This is optional if you are not in the 205L. If you are in the 205L, then this is required that you download the class notes, um, fill them out, and send them in as a PDF, just like your homework. And this will be due next Tuesday. Okay, so review of sequences and series. So we'll start with just some vocabulary. So a sequence is just a function whose domain is a subset of natural numbers. So typically you could use 1, 2, 3, 4, and so on, or 0, 1, 2, 3, 4. You could start at 0, you could start at 1, not a big deal. We're going to start at 1. The outputs of a sequence are called the terms of the sequence. And when we list the terms of the sequence, it is understood that the first number is the output when the input is 1, the second number is the output when the input is 2, and so on. So a sequence is just a function. We're only allowing of integer inputs that are, or whole number inputs, I should say. And so we have function notation where we have the name of the function is here. The input variable goes inside the parentheses, and on the other side we have the rule. So a function is just a rule that assigns to each input only one output, and we use function notation to write our rules. But for sequences, we've developed different notation. Instead of putting the input in parentheses, we write the input down here as a subscript. And so we read that A sub n, or AN is fine, but I read it A sub n. The name, uh, instead of F, G, or H, we typically give the name of sequences A, B, C. You can call it whatever you want. There's really no reason why you couldn't write F, but typically we use F, G, and H for functions, and A, B, and C for sequences. And our input variable, instead of being an X, it's an N. So A sub n is 3n plus 4. The 3n plus 4 is just the rule. A sub n is called the general term, right? So the general term, and 3n plus 4 is the rule or the formula. So write the first 5 terms of the sequence whose general term A sub n is 5n. So when we were working with functions, there's no such thing as a first term unless your domain is a closed interval. Has a closed left endpoint. But with sequences, in our class, the first term is going to be the output when the input is 1. So we could make a table, n and a sub n, and we have 1 time, we put that into the formula, and we get 5, 2 times 5 is 10, 3 times 5 is 15, 4 times 5 is 20, and 5 times 5 is 25. But rather than making a table, we can just list out the terms, because it's understood that the first one is the output when the input is 1. The second one is the output when the input is 2, 15, 20, 25, and this is how we will do it. So go ahead and pause the video and do the next one. Write the first 5 terms of the sequence whose general term is 3n. So again, 3n, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15. What you're looking at there, 3, 6, 9, 12, 15 are the multiples of 3, and that's what this is. It's 3 times n. Since they are the multiples of 3, they go up by 3. So 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, 12 plus 3 is 15. Or another way of looking at it, anytime you subtract 2 consecutive terms, you get 3. 6 minus 3 is 3, 9 minus 6 is 3, 12 minus 9 is 3, 15 minus 12 is 3. In this problem, we have 6n minus 2. Without the minus 2, we would be looking at the multiples of 6, but now they have a minus 2. So 6 times 1 is 6, minus 2 is 4. 6 times 2 is 12, minus 2 is 10. 6 times 3 is 18, minus 2 is 16. 6 times 6 times 4 is 24, minus 2 is 22. 6 times 5 is 30, minus 2 is 28. So although we do not have the multiples of 6, because we subtracted 2 from each of them, we have 2 less than the multiples of 6, but we are still going up by 6. The difference of any two consecutive terms is going to be 6. So when you look at formulas that look like this, this tells you what you're going to go up by each time. And this minus 2 just tells us where we start. 6 times 1 is 6. Minus 2 is 4, so we're going to start at 4 and go up by 6. 4, 10, 16, 22, 28, and no need to use the formula. And every time, 6 times 1 minus 2, 6 times 2 minus 2, and so on. Write out the first 5 terms of the sequence whose general term a sub n is n squared. Right? So again, at each one of these phases, you should pause the video and then hit play. Okay, so n squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. You should be familiar with this sequence. These are just the squares. And the squares are interesting because first they go up by 3, then they go up by 5, then they go up by 7, then they go up by 9, then they would go up by 11. You know the next one is 36. Then they go up by 13. You know the next one's 49. That's kind of cool. So when you see something that's going up by 3, 5, 7, 9, 11, it might have something to do with the squares. We'll write out the first 5 terms of the sequence whose general term is a sub n is equal to negative 1 to the n divided by 2n plus 3. So every time you're going to get a fraction, one, two, three, four, 5. On the bottom, we have 2n plus 3. So again, because of the 2n plus 3, that you're going to go up by 2. So 2 times 1 is 2, plus 3 is 5. But then it'll be 7, 9, 11, and 13. 2 times 5 is 10, plus 3 is 13. We could get there that way too. In the numerator, you have this negative 1 to a power. Negative 1 to the first power is negative 1. Negative 1 to the second power is positive 1. Negative 1 to the third power is negative 1. Negative 1 to the fourth power is positive 1. Negative 1 to the fifth power is negative 1. And so then all this does is gives you a factor of either negative 1 or 1. It's a negative 1 when the power is odd, and it's a positive 1 when the power is even. And so then in a little bit, we're going to start building our own sequences. And so we're going to want to know how to get different factors, different pieces. Okay, so write out the first 5 terms of the sequence whose general term is a sub n is equal to negative 1 to the n plus 1. So again, every term is going to be a fraction. In your denominator, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. In the numerator, negative 1, when we put in 1 for n, you'll get negative 1 to the second power, which is positive 1. Negative 1 to the third power is negative 1. Negative 1 to the fourth power is positive 1. Negative 1 to the fifth power is negative 1. Negative 1 to the sixth power is positive 1. And so you can see again that all this does is give us an extra factor of negative 1 or 1, depending on whether the exponent is even or odd. With the n plus 1, it starts out even, so you start positive, negative, positive, negative, positive. So write the first 5 terms of the sequence whose general term is 2 to the n. So 2 to the n, 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8, 2 to the 4th is 16, 2 to the 5th is 32. When the variable's in the exponent, whatever your base is, you're going to change by a factor of that. So since my base is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16, 2 times 16 is 32. So these exponentials, that is how they grow. So in this next example, we have three different sequences. Again, going over what's the point behind giving these things names, so that if you have more than one sequence or more than one function, then you know which one to use. So a sub n, the formula is n plus 1 divided by n squared. B sub n is 3 times n plus 5, and c sub n is 3 to the n. So to find the fourth term, c sub 4, you just simply go to your formula for c, and you put in 4, and you get 3 to the 4th power. And 3 to the 4th power is 81. To find a sub 5, you go to your formula for a, and you replace n with 5. 5 plus 1 divided by 5 squared, 6 over 25. B sub 7, just go to your formula for b, replace n with 7, 3 times 7 plus 5. 21 plus 5, 26. One of the things I'm going to need you to be able to do is come up with formulas for lists of numbers, for sequences. And so here we have this list that you should be familiar with. These are the even numbers, and all it means to be even is that it's a multiple of 2, 2, 4, 6, 8. They're going up by 2. They're the multiples of 2. And so then we just write a sub n is 2n. You should try these on your own. Find the general term for the sequence 3, 5, 7, 9. These are the odds, except we don't have 1. But you can see that they're still going up by 2. When they're going up by 2, then it has something to do with 2n. But 2 times 1 is 2. And then add 1 and you get 3. And let's make sure it works for the second one. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6. Plus 1 is 7, and 2 times 4 is 8, plus 1 is 9. It works for all of them. Okay, now there turns out that there are more complicated formulas that will generate these first 4 terms, but we're looking for the most basic one. So you should pause, try this on your own. This is all just pattern recognition, your familiarity with these different lists that we've used throughout these last years. 4, 9, 16, 25, those are all squares. We're just missing the first one. So we're squaring. But we want to start with 2 and then 3 and then 4 and then 5. So we don't want to square just n. If we first add 1 and then square, we will generate the formula. Now when n is 1, 1 plus 1 is 2, squared is 4. When n is 2, 2 plus 1 is 3, squared is 9. When n is 3, 3 plus 1 is 4, squared is 16. And when n is 4, 4 plus 1 is 5, squared is 25. Here, 2, 5, 10, 17, we notice that we first go up by 3, then by 5, then by 7. So this should bring to mind, hey, the n squared did that. But when I square 1, I get 1, and I want 2. Well, I could fix that by adding 1. But now when I square 2, I get 4, plus 1 is 5, works for that one. 3 squared is 9, plus 1 is 10, works for that one. 4 squared is 16, plus 1 is 17, works for that one as well. Now we want to find the general term for this sequence, right? So again, pattern recognition is all we're going over. Notice that each term is a fraction, so put your fraction bar in the numerator. Each term has a numerator of 1, and all that changes is the denominator. So we can just now focus on the denominators. 5, 10, 15, 20. You notice that they're multiples of 5. 5n. Again, pattern recognition. And what we want to do is just look at it one piece at a time. We have this negative, positive, negative, positive. So again, we get that from a factor of -1 to the n, or to the n plus 1. Since we want to start negative, when n is 1, we want it negative, so we want it odd, so we leave it alone, n. Then we've got a fraction. In your numerator, you have 1, 4, 9, 16, so that would just be n squared. In your denominator, you have 7, 14, 21, 28. That would be 7n, the multiples of 7. And there you go. For this one, 3, 6, 9, 12. Let's handle the easy part first. 3, 6, 9, 12, multiples of 3. 1, 5, 25, 125. Notice these go up by a factor of 5. And so then that tells us that it might be 5 to some power. 5 to the 1 is 5 though. We want that 1 second. 5 to the 2 is 25. We want that 1/3. 5 to the 3rd is 125. We want that 1/4. 1, 2, 3, 4. So we're off by 1. So if we just take 1 away, then we'll start at the right spot. And now we have positive, negative, positive, negative. Well, that's again our factor of -1. And then we could, if we start at n, when n is 1, we'll get a negative, and we want a positive. So we have to do the n plus 1 for that one. And there we go. Build it one step at a time. Okay. So an auditorium has 10 seats in the first row, and each row has 3 more seats than the row before it. List the sequence of the number of seats in each row if there are 9 rows. How many seats are in the auditorium? An auditorium has 10 seats in the first row, so the sequence of number of seats starts with a 10. And each row has 3 more seats than the row before it. So the next one is 13, and then 16, and then 19, and then 22, and then 25. 1, 2, 3, 4, 5, 6, 28, 31. 1, 2, 3, 4, 5, 6, 7, 8. One more. 34. List the sequence of number of seats in each row if there are 9 rows. So in this case, the sequence, the term number just represents how many seats are in that row. So the first term number is 10 because there's 10 seats in that first row. The second term number is 13. And so that means that in the second row, there's 13 seats, and so on and so forth. How many seats are in the auditorium? Okay, well, sometimes what we're going to want to do with these numbers is we're going to want to add them up. And here's an example of why, in the context of this problem, adding them up gives us the total number of seats. So we would take 10 plus 13 plus 16 plus 19 plus 22 plus 25 plus 28 plus 31 plus 34. Even with a calculator, that could take a little bit. But if you notice, if you add 10 and 34, you get 44. If you add 13 and 31, you get 44. If you add 16 and 28, you get 44. If you add 19 and 25, you get 44. So you get 1, 2, 3, 4 44s. And 22. 198. There are 198 seats in this auditorium. So again, we need some more vocabulary. definition, the sum of the terms of a sequence is called a series. So when we have a series, we're adding up the terms of a sequence. So find the sum of the first 6 terms of the sequence whose general term a sub n is 2n plus 3. So here we're going to take this sequence, a sub n is 2n plus 3, and make the series by adding up the first 6 terms. Again, notice that this 2n here, that's telling you that you're going to go up by 2. But when you put in 1, you get 5, plus 7, plus 9, plus 11, plus 13, plus 1, 2, 3, 4, 5, plus 15. This one and this one make 20. This one and this one make 20. And this one and this one make 20. We have 3 pairs of 20. This sum is 60. Now find the sum of the 3rd through the 8th term of the sequence whose general term is 3n minus 4. And so again, 3n minus 4, these simple formulas where it's a constant times n plus a constant or minus a constant are going to go up by whatever number this is. So the 3rd term is 3 times 3 is 9, minus 4 is 5. And then 8, and then 11, and then 14. So 3rd, 4th, 5th, 6th, I need 2 more, and then 17, and then 20. These 2 pair up to 25, these 2 pair up to 25, and these 2 pair up to 25. We have 3 pairs of 25, 3 times 25, 75. Now, so a big part of mathematics is all this notation that we make up to make things easier to write. And you have to get used to it. So this is why I'm reviewing it. You should have learned all this in pre-calculus, but that's been a while, so let's review it. So when we want to add up the terms of a sequence, we get a series, and then we made up summation notation so that we don't have to write so much. So summation notation. The way you read this is this symbol, you read the summation from I equals 1 to I equals 6 of 2i plus 3. And what that means is the sum of the first 6 terms of the sequence whose general term is 2n plus 3. So when you see summation notation, right, you have this bottom down here, I equals 1. This is the I is the index of summation. The number over here, the 1, is the term number you start with. We don't always start at 1. As I did in that second example, you could start at 3 or whatever number you want to. The number up on top is the term number you end with. The formula after the summation notation, that's where you're getting your terms from. You put in the 1, the 2, the 3 into the 2i plus 3. And so we're here, evaluate the summation from I equals 1 to 4 of I squared. This means plug in 1 into the formula, you get 1. Plug in 2 into the formula, you get 4. Plug in 3 into the formula, you get 9. Plug in 4 into the formula, you get 16, and you stop when you plug in 4. Now you add those up. Those 2 make 10, and those 2 make 20, and so the answer is 30. Sometimes we'll start at 0 instead of 1. No big deal, just same thing. From the summation from I equals 0 to 5 of 2 to the I. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. And 2 to the 5 is 32. This number up here does not mean the number of terms. This number up here means the last term number that you plug in. So we're plugging in, start with 0, 1, 2, 3, 4, 5. After you plug in the 5, you stop. Those 2 make 10. Those 2 make 20. And so that makes 30. 30 and 32 make 62, 63. The summation from I equals 0 to 5 of I plus 3 over 3, right? People see fractions and they start to panic. No need to panic. You're going to start with 0. So then you're going to get 0 plus 3 is 3 over 3. The number in front is 1. So that means that your terms are going to go up by 1. So then you have 4 over 3, and then 5 over 3, and then 6 over 3, and then 7 over 3, and then 8 over 3. This is a quick way of writing it, but you need to be careful. You have to stop when you've plugged in 1. So that was plugging in 0, 1, 2, I'm sorry, when you've plugged in 5. That was plugging in 0, 1, 2, 3, 4, and this is plugging in 5, so you're done. And now the 3 and the 8 make 11, the 4 and the 7 make 11, the 5 and the 6 make 11. So you have 3 pairs of 11, so you have 33. The denominator was always the same, so you just use the same denominator, and so you end up with 11. Don't have to start at 0 or 1. We could start at 3. The summation from I equals 3 to 5 of I cubed. Plug in 3, you get 27. You plug in 4, you get 64. You plug in 5, you get 125. Don't have a quick way of adding those, so we just reach for the calculator. 27 plus 64 plus 125, 216. We're going to need to be able to go backwards. We're going to need to be able to give you a series and you write it in summation notation. So that puts together the two things there. So write the series in summation notation. It's not asking you to find the sum. It's asking you to write the series in summation notation. So we have 7 to 12 is 5. 17 minus 12 is 5. 22 minus 17 is 5. 5, 5. Every time you're going up by 5. So then this should tell you that your terms are generated by the formula 5n plus something. So to get the 7, we need a plus 2. Make sure that it works for the other ones. 5 times 2 is 10, plus 2 is 12. We got that one. 5 times 3 is 15, plus 2 is 17. We got that one. 5 times 4 is 20, plus 2 is 22. We got that one. 5 times 5 is 25, plus 2 is 27. So this formula works. But this is a series. This is a sequence. We want to write the series in summation notation. So for summation notation, the name of your counter makes absolutely no difference. But for some reason, a lot of books, and now I have that habit, when I write the sequence, I use n, and when I write the series, I use a different number. So I'm going to use I equals 1. No need to start anywhere else. To get the 7, we plug in 1. And to get the 32, we plug in 5. I'm sorry, we plug in 1, 2, 3, 4, 5, 6. To get the 32, we plug in 6. 5 times 6 is 30, plus 2 is 32. And the formula, because we use I as my counter, then needs to be 5i plus 2. And there we go.